In every age, humanity has turned its gaze upward, searching for meaning in the faint light scattered across the night sky. The stars have always been there, constant, silent, and impossibly distant. Yet our understanding of them has never stood still. For thousands of years, we believed the heavens were fixed, perfect, untouchable. Then one invention, a simple tube of glass and metal, changed everything. The telescope transformed the sky from a tapestry of mystery into a landscape we could explore. But even as our eyes grew stronger, the universe revealed only a fraction of itself. What we call light is merely a whisper in an infinite chorus of invisible energy. Beyond the colors we can see lies a vast electromagnetic spectrum. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, each one carrying secrets that our eyes alone could never perceive. To understand the cosmos, we had to learn to see without seeing, to imagine vision that transcends the limits of biology. From the earliest radio antennas that hissed with signals from the Milky Way to the orbiting eyes of Hubble, Chandra, and Spitzer, each new way of observing has revealed a different universe, one of violent explosions, invisible clouds, and cosmic architecture stretching billions of light-years across space. It is a universe both familiar and alien, where the visible is only the surface of something deeper and more dynamic. And yet, as our instruments reach farther, a new mystery begins to emerge. What if the universe we see, the bright stars, the glowing nebulae, the swirling galaxies, is only a thin veil? What lies hidden in the darkness between? Could there be forces, structures, even forms of light that exist entirely beyond our perception? This is the story of how we learned to see the unseen, how light itself became our guide through time and space. It is a journey through invention and imagination, through the deserts of Earth and the void beyond, as humanity opens its most powerful eyes and dares to look farther than ever before. It began, as many discoveries do, with a sound that no one expected. In 1931, an engineer named Karl Jansky was working for Bell Telephone Laboratories in New Jersey. His task was simple: to identify sources of static that might interfere with long-distance radio communication. To do this, he built a massive rotating antenna, an ungainly contraption made of metal tubes and wires, turning slowly in a field. Day after day, Jansky recorded the crackles and hisses that filled his receiver, mapping them to passing thunderstorms, distant signals, and background noise. But one hiss would not go away. It was constant, faint, and strangely periodic. After months of patient analysis, Jansky realized that the mysterious signal reached its peak not once every 24 hours, but every 23 hours and 56 minutes. The length of a sidereal day, the time it takes Earth to rotate once relative to the stars. Whatever was producing this faint radio whisper, it wasn't coming from the Earth at all. It was coming from space. Without knowing it, Jansky had opened a new window on the cosmos. The universe, it turned out, was speaking not just in visible light but in radio waves. Long, invisible ripples of energy that could pass through clouds, dust, and darkness. Yet his discovery was largely ignored. Astronomers of the 1930s were still bound to optical telescopes. Radio technology was seen as the domain of engineers, not explorers of the heavens. That changed with another man, Grote Reber, an amateur astronomer with a knack for electronics. In his backyard, he built the world's first true radio telescope, a 9-meter-wide metal dish aimed at the sky. While others looked through eyepieces, Reber listened, and what he found transformed our cosmic map forever. Through radio eyes, the Milky Way shone with a cool, ghostly glow. Entire regions of the galaxy that had been hidden behind thick curtains of interstellar dust suddenly came alive. The invisible became visible. Radio astronomy had begun, and with it, a revolution in how humanity understood its place in the universe. Soon, astronomers realized that these radio signals weren't just noise. They were fingerprints, each wavelength revealing a different kind of process, a different form of cosmic energy. Hydrogen gas, supernova remnants, and the blazing jets of matter spiraling from black holes all left their marks in the radio spectrum. By the middle of the 20th century, humanity's ears had become our newest eyes. We could now trace the spiral arms of our galaxy, study its hidden core, and even detect the faint radio murmur left behind from the birth of the universe itself, the cosmic microwave background. But for all the power of radio waves, they were only the beginning. The universe had far more to say, in forms of light we had yet to learn how to see. For centuries, we imagined light as something simple, a golden bridge between the stars and our eyes. Yet light is not a single thing. It is energy, vibration, and information all at once. What we perceive as color is merely a small fragment of a far greater spectrum that stretches far beyond human vision. The human eye can detect wavelengths from roughly 390 to 750 nanometers, what we call visible light. Within that narrow range lie all the colors of the rainbow: violet, blue, green, yellow, orange, and red. But light extends much farther. Longer wavelengths become invisible radio waves and microwaves, while shorter ones transform into ultraviolet rays, X-rays, and the deadly brilliance of gamma radiation. Each of these invisible forms of light tells a different story about the universe. Where our eyes see only darkness, infrared reveals the soft heat of stars being born. X-rays expose the violent aftermath of supernova explosions. Radio waves trace the cold hydrogen skeleton of galaxies. Gamma rays, the shortest and most energetic of all, illuminate the universe's most catastrophic events: the birth of black holes, the annihilation of matter, and perhaps the echoes of creation itself. Our first step into this hidden universe came from necessity. Earth's atmosphere, the same shield that makes life possible, blocks most wavelengths of light. It protects us from lethal radiation but blinds us to much of the cosmos. For astronomers, this meant only one solution: to leave the ground behind. In 1990, the Hubble Space Telescope was launched into orbit, carried aloft by the Space Shuttle Discovery. Hubble's cameras were designed not only to see what the human eye could see, but to peer slightly beyond into the ultraviolet and near-infrared. Suddenly, the cosmos unfolded with unprecedented clarity. Hubble's images revealed the births of stars inside dusty nebulae, the swirling arms of galaxies tens of millions of light-years away, and even faint glimpses of the early universe, when the first galaxies were just beginning to form. But Hubble was only the beginning of humanity's great migration into the invisible. The Chandra X-ray Observatory opened our eyes to high-energy events, where temperatures reached millions of degrees. The Spitzer Space Telescope mapped the universe in infrared, unveiling cold clouds of dust and the hidden embryos of newborn stars. GALEX, the Galaxy Evolution Explorer, studied ultraviolet light to track how galaxies form and age across cosmic time. Each of these telescopes gave us a different version of reality. Look at the same galaxy through optical light, and you see a swirl of luminous stars. View it in infrared, and it becomes a web of dust and shadow. In X-rays, it bursts into a storm of high-energy radiation, a battlefield of dying stars and devouring black holes. Together, these instruments built a mosaic, a cosmic rainbow invisible to our eyes but vital to understanding everything we see. And yet, the more we expanded our vision, the more we realized how much remained hidden. What if, beyond even these wavelengths, there are realms of light we cannot yet detect? Forms of energy that slip past our instruments the way infrared light once slipped past Galileo's eyes? If seeing is understanding, then our search to comprehend the universe is, at its heart, a search to see more deeply. Each new eye we build, each telescope, satellite, and sensor, brings us one step closer to unveiling the true face of reality. Beyond the gentle shimmer of visible light lies a universe of violence. Here, stars explode, atoms shatter, and gravity itself bends space into oblivion. This is the domain of high-energy radiation, X-rays and gamma rays, forms of light so powerful that they can pierce through entire galaxies, yet remain invisible to the human eye. To detect such light, astronomers had to overcome one of nature's most protective barriers: Earth's atmosphere. Our planet's thick shell of gas blocks almost all X-rays and gamma rays, shielding us from deadly cosmic radiation. To see the universe in this new light, telescopes had to leave Earth behind. In 1999, NASA launched the Chandra X-ray Observatory, one of the most ambitious instruments ever sent into orbit. Unlike traditional telescopes with curved mirrors, Chandra uses nested cylinders coated with iridium to gently deflect X-rays into its detectors. Only with such delicate precision can it collect the faintest whispers of high-energy light from across the cosmos. What Chandra revealed was astonishing. The night sky, once imagined as tranquil, was instead a landscape of turmoil. Everywhere it looked, it found violence. Supernova remnants glowing like frozen fireworks, black holes feeding on the gas of nearby stars, and clusters of galaxies bound together by colossal storms of million-degree plasma. Near the center of our Milky Way, Chandra discovered something even more extraordinary. A region of chaos, hidden behind thick veils of dust that block optical light. Through X-rays, that darkness became transparent. What emerged was a seething panorama of hot gas, neutron stars, and magnetic mayhem, all swirling around a single, bright point of energy. Astronomers soon realized what they were seeing. The glowing accretion zone of Sagittarius A*, the supermassive black hole at the heart of our galaxy. From that moment on, the Milky Way was no longer viewed as a quiet collection of stars, but as a living, breathing ecosystem, one shaped by the immense gravitational pull and radiation of its central black hole. While Chandra peered into this hidden inferno, another observatory extended our reach even further. In 2008, NASA's Fermi Gamma Ray Space Telescope was launched to explore the most energetic phenomena in the universe. Instead of mirrors, Fermi uses layers of metal to capture incoming gamma rays, tracking their direction and energy as they collide and split into pairs of matter and antimatter. The results challenged everything we thought we knew. Fermi detected enormous bubbles of high-energy radiation erupting from the center of the Milky Way, each one tens of thousands of light-years tall. The source of these cosmic outbursts remains a mystery. Were they ancient explosions from Sagittarius A*, or echoes of star formation so intense it reshaped our galaxy? Fermi also caught fleeting bursts of gamma rays appearing at random points across the sky, explosions so powerful they outshone entire galaxies for a few seconds. These gamma ray bursts are believed to mark the births of black holes, moments when massive stars collapse in on themselves and release unimaginable energy. In this violent light, the universe is no longer serene. It is alive, restless, and constantly remaking itself. The calm glow of the stars we see with our eyes hides a cosmos of unimaginable extremes, one where destruction and creation are two sides of the same process. And yet, for all the fury of X-rays and gamma rays, they reveal only the hottest and most energetic parts of existence. To understand the universe's quieter, cooler side, the slow birth of stars, the gentle folding of galaxies, we must turn our gaze to longer wavelengths, to light we can feel as warmth but never see. Long before stars ignite and galaxies blaze, the universe whispers in warmth. That warmth, soft, silent, and invisible, travels through space as infrared light, a form of energy that our skin can feel but our eyes cannot see. It is the light of dust, of cool gas, of cosmic structures still in the process of becoming. And for astronomers, it is the key to unlocking the universe's most elusive secrets. Infrared astronomy began as an experiment, a way to look through the smoke and shadows of the cosmos. While visible light bounces off dust and vanishes into darkness, infrared radiation passes through, revealing what lies beyond. This invisible illumination allows us to peer into the hidden cradles of star formation, into the hearts of galaxies shrouded in cosmic fog, and even into the earliest epochs of creation. But once again, Earth's atmosphere stood in the way. Water vapor and carbon dioxide absorb most infrared light before it reaches the ground. The solution, as it so often is in astronomy, was to rise above the air itself. In 2003, NASA launched the Spitzer Space Telescope, a mission designed to explore the universe in infrared. Spitzer's delicate instruments were cooled to near absolute zero, allowing it to detect faint heat signatures billions of light-years away. What it revealed was astonishing. Dark nebulae that glowed softly with the warmth of newborn stars, galaxies bursting with dust and energy, and distant worlds orbiting other suns. Through Spitzer's eyes, even familiar objects appeared transformed. The North America Nebula, a cloud of gas and dust faintly visible from Earth, revealed vast glowing tendrils and hidden pockets of star birth when seen in infrared. Regions that once seemed empty in visible light became intricate webs of heat and dust, each thread a potential nursery for new suns and planets. Soon, other instruments joined in. The Herschel Space Observatory, launched by the European Space Agency in 2009, looked even deeper into the infrared spectrum, detecting cooler objects than Spitzer ever could. Herschel's massive mirror, the largest ever sent into space at the time, gave us our first clear views of the cold universe. Regions where temperatures hover just a few degrees above absolute zero. Within those icy clouds, matter slowly gathered, twisted, and condensed under gravity's pull to form the first seeds of stars. When Herschel turned its gaze on the Andromeda Galaxy, our nearest major neighbor, the familiar spiral faded. Instead of bright stars, Herschel revealed glowing filaments of dust, ribbons of material stretching across thousands of light-years, tracing the structure of the galaxy's spiral arms like veins of gold beneath skin. Infrared light became a bridge between the invisible and the seen, a language spoken by the coldest parts of the cosmos. It allowed astronomers to study the earliest stages of star formation, to find young exoplanets still glowing from the heat of their birth, and to look across billions of years to when the first galaxies flickered into existence. Today, this legacy continues with the James Webb Space Telescope, humanity's most ambitious attempt to see the unseen. Webb peers deeper into the infrared than any telescope before it, using its golden mirrors and cryogenic instruments to capture light that has traveled across 13 billion years of time. With each image, it carries us closer to the moment of the universe's awakening, the dawn of stars, the first light that ever shone. Infrared light teaches us that creation does not begin with fire, but with warmth, with slow, patient energy building in silence until it bursts into brilliance. Yet, as we learn to see the heat of the cosmos, another kind of light calls to us. A faint radio whisper that fills all of space, coming not from stars or galaxies, but from the birth of time itself. It was a discovery that began, as so many cosmic revelations do, by accident. In 1964, two engineers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna designed for satellite communications. Their equipment was precise, their calibration meticulous, yet something was wrong. A faint, persistent hiss filled their receivers, a noise that came from every direction and refused to disappear. They cleaned the antenna, chased away nesting pigeons, checked the electronics, but the hiss remained. Finally, after consulting with physicists at Princeton University, they realized what they had found was not a malfunction. It was the oldest light in the universe, the cosmic microwave background radiation, or CMB. This faint, uniform glow was the aftershock of creation itself, the remnant heat left behind by the Big Bang nearly 14 billion years ago. When the universe was young, dense, hot, and filled with searing plasma, light could not travel freely. Photons scattered endlessly among charged particles, trapped in a cosmic fog. But as the universe expanded and cooled, atoms began to form, and light at last broke free, racing outward in all directions. That light has been traveling ever since, stretched by the expansion of space into the cold, invisible microwaves that now fill the cosmos. To the human eye, the sky is dark, but if we could see in microwaves, it would glow softly, evenly, and everywhere. The discovery of the CMB confirmed one of science's most profound ideas, that the universe had a beginning. This wasn't just a random hiss of energy. It was the first light, fossilized and preserved in every corner of the sky. For the first time, scientists could glimpse what the cosmos looked like when it was just 380,000 years old, a newborn universe. Over the decades, satellites like COBE, WMAP, and most recently Planck have mapped this cosmic background in exquisite detail. What once appeared uniform now reveals delicate variations. Tiny fluctuations in temperature, only millionths of a degree apart. Yet these small ripples carry immense meaning. They are the fingerprints of the first structures in the universe, the seeds from which galaxies, stars, and planets would one day form. The CMB is a message written in ancient light, one that tells us how the universe was shaped. Its patterns reveal the density of matter and dark energy, the curvature of space, and even the age of the cosmos itself. Each new measurement brings us closer to answering questions as old as existence. What caused the Big Bang? What existed before? And why is there something rather than nothing? But the CMB is not just a relic. It's a bridge. It connects every moment of cosmic history, from the first instant of creation to the galaxies we see today. It is the quiet hum beneath all of existence, a universal heartbeat that never fades. And so, in the space of a few decades, humanity had gone from gazing at stars to hearing the echo of the birth of everything. Yet, while the cosmic background revealed our beginning, it also hinted at our limits. Beyond that faint glow lies a realm we may never see, regions of space so distant that their light has not yet reached us. There, perhaps, the universe continues infinite and eternal, beyond the horizon of time. But before we could grasp the full scale of that infinity, we needed to turn our eyes back to Earth, to the deserts, mountains, and frozen plateaus where humanity was building the most powerful telescopes the planet had ever known. In the far north of Chile, where rain rarely falls and the landscape seems carved from another planet, a desert stretches between mountains and sky. This is the Atacama Desert, the driest place on Earth, and perhaps the most extraordinary observatory nature ever created. Here, at altitudes above 2,500 meters, the air is so thin and clear that the stars appear unnaturally bright. On most nights, there are no clouds, no humidity, and no light pollution. Only the steady brilliance of the Milky Way arching overhead. For astronomers, the Atacama is nothing less than a doorway to the cosmos. The transformation of this barren landscape into a world capital of astronomy began quietly in the late 20th century. As telescopes grew larger and more precise, they demanded perfect conditions. Air stable enough to prevent starlight from blurring and skies dark enough to reveal even the faintest glow of distant galaxies. Chile's mountains offered all of that and more. Perched high above the desert floor on a mountain called Cerro Paranal, stands one of the most advanced optical observatories on Earth, the Very Large Telescope, or VLT. Despite its modest name, it is not a single telescope, but an array of 4 giant 8.2-meter mirrors, each capable of working independently or together as one. When combined, their collective vision rivals the clarity of even the Hubble Space Telescope. But to achieve that precision, the VLT must perform an extraordinary feat of engineering. Each of its thin, delicate mirrors, barely 20 centimeters thick, would bend under its own weight if left unsupported. To prevent this, every mirror rests on a web of 150 tiny actuators, mechanical fingers that subtly flex and adjust the glass hundreds of times per second, countering the distortions caused by gravity and temperature. Even the atmosphere itself, our greatest barrier to perfect sight, is now part of the equation. Using a technology known as adaptive optics, the VLT projects a laser beam into the sky, creating an artificial guide star. By measuring how the atmosphere distorts the returning light, computers deform a secondary mirror in real time, canceling the turbulence of the air. The result is a view so sharp it can capture the motions of individual stars orbiting the black hole at the center of our galaxy. And that is exactly what it has done. For over 2 decades, the VLT has tracked these stars as they whirl around an invisible center, their paths curving under the immense pull of Sagittarius S star. These precise measurements, each one a testament to both human ingenuity and cosmic mystery, proved that a supermassive black hole lurks just 26,000 light-years from Earth. But Paranal is not alone. Across the Atacama, a new generation of telescopes rises from the dust, each designed to explore the universe in a different form of light. The most ambitious of all sits even higher, nearly 5 kilometers above sea level, where the air is almost completely free of water vapor. There, among the peaks of the Andes, astronomers have built the Atacama Large Millimeter/Submillimeter Array, known simply as ALMA. ALMA does not look like a telescope in the traditional sense. It is a field of 66 gleaming white antennas, each one 12 meters wide, spread across a plateau the size of a small city. Working together, these dishes act as a single giant instrument, observing the universe in the faint millimeter wavelengths that lie between infrared light and radio waves. In this hidden range of the spectrum, ALMA can see what no other telescope can: the coldest, most delicate structures in space. The birthplaces of stars, the disks of gas forming new planets, and the faint glow of galaxies from the earliest cosmic dawn. From the heart of this desert, where not even rain can endure, humanity is learning to see the beginnings of everything. And yet, the Atacama story is not just about technology. It is about perspective. Here, surrounded by silence and sky, we are reminded that the quest to understand the universe always begins in the same place, with a human looking up. Every great telescope begins as a dream. Before it sees a single star, it exists only as an idea, a fragile bridge between imagination and the laws of physics. To build one is to take on the universe itself, to shape glass so perfect it bends light without error, to control machinery that can point with subatomic precision, and to tame an environment that constantly shifts between chaos and calm. In this way, astronomers are not just explorers of the sky. They are architects of vision, crafting instruments that allow humanity to perceive what nature never intended us to see. When we look at the modern landscape of astronomy, from the deserts of Chile to the frozen plateaus of Antarctica, what we find is a network of machines so complex that they border on the poetic. Each one is a cathedral of technology, built in service of curiosity. At Cerro Paranal, the very large telescope stands as the centerpiece of this vision. Its 4 main units, named Untu, Kian, Melipal, and Yepen words for celestial objects in the Mapuche language of Chile, work in concert like a symphony. Using interferometry, their combined light is merged through underground tunnels, producing the sharpness of a single mirror more than 100 meters wide. With this technique, astronomers can resolve details as small as the surface of a star hundreds of light-years away. But even such precision is only the beginning. The next generation of telescopes is already taking shape. Machines so vast they will redefine what it means to see. On a nearby peak in the Atacama, construction is underway for the Extremely Large Telescope, ELT, an optical instrument with a 39-meter main mirror composed of nearly 800 hexagonal segments. When complete, it will be the largest eye ever turned to the heavens. With adaptive optics sharper than Hubble and light-collecting power 100 times greater, the ELT will allow us to directly image Earth-like exoplanets, watch the growth of galaxies across cosmic time, and perhaps glimpse the first stars that ever formed. The design of such instruments pushes the limits of engineering. Each mirror segment must align with micron-level accuracy, adjusting hundreds of times per second to maintain a perfect shape against wind, gravity, and temperature. The telescope's dome, large enough to hold a cathedral, rotates smoothly on air bearings, while computers predict and correct atmospheric distortions faster than the human eye can blink. And while the ELT captures visible and infrared light, other projects aim to reach where even that cannot go. The Square Kilometre Array, SKA, soon to stretch across the deserts of South Africa and Western Australia, will be the most powerful radio observatory in history. With thousands of antennas working together across continents, it will peer into the cosmic dark ages, the time before the first stars lit up the universe. Each of these instruments represents a triumph of collective ambition. Nations, universities, and private institutions across the globe contribute materials, knowledge, and expertise, united by a single purpose: to extend humanity's perception into the unknown. But behind every mirror and dish lies something more profound, a belief that vision itself can evolve. The telescopes we build do not just reflect light, they reflect us. They embody the human impulse to reach beyond limits, to turn curiosity into machinery, and machinery into revelation. It is not lost on astronomers that the act of building a telescope mirrors the act of creation. To craft such an instrument is to imitate the universe, to harness gravity, heat, and light, and give them form. In a sense, every observatory is a small universe unto itself, born of chaos, shaped by order, and guided by the invisible forces of imagination. Yet even the greatest telescopes can only capture what light allows. To explore the unseen, to find meaning in the shadows, we must also learn to interpret the signals, translating raw data into vision, and vision into understanding. Seeing in astronomy is never just a matter of light. It is also a matter of translation. Every telescope, whether it captures radio waves, visible light, or gamma rays, gathers not beauty, but data. Numbers, pulses, photons recorded on sensors. What we later call an image is, in truth, a human creation. An interpretation of those signals shaped by algorithms, color maps, and imagination. In this way, astronomers do not merely observe the universe, they rebuild it. Consider the images from the Hubble Space Telescope. Their colors, so vivid and hypnotic, are not what the human eye would see in space. They are the result of assigning visible hues to invisible wavelengths, transforming streams of data into works of art. Each shade of red, green, and blue represents a different chemical signature: hydrogen, oxygen, sulfur, painted across the canvas of the cosmos. These false colors reveal real truths: regions of star birth, explosions of dying suns, or the swirling chaos of galaxies colliding. The same is true for telescopes across the spectrum. The Chandra X-ray Observatory shows the universe as a storm of plasma, rendered in brilliant violet. Spitzer and Herschel depict it as a glowing web of dust and warmth. Fermi captures the cosmos in gamma rays, where every flash marks an act of violence on a scale we can scarcely imagine. But transforming light into knowledge requires more than artistry. It demands computation. Modern astronomy produces petabytes of data each year, more than humanity can comprehend without the help of supercomputers. The Atacama's ALMA array alone generates enough information daily to fill entire libraries. To manage this flood, astronomers rely on advanced processing systems, digital minds that can filter, reconstruct, and correlate signals from dozens of antennas spread across kilometers. Through this synthesis, a radio wave collected in Chile can be combined with another received in Hawaii, creating a telescope the size of Earth itself. This technique, known as Very Long Baseline Interferometry, VLBI, has allowed scientists to capture the unseeable, a photograph of a black hole. In April 2019, the world saw it, the blurred orange ring of Messier 87's black hole, 55 million light-years away. It was not taken by a single telescope, but by an entire planet acting as one. The Event Horizon Telescope combined data from observatories on multiple continents, synchronized by atomic clocks so precise they lost less than a second in 100 million years. What the image showed was more than a scientific triumph. It was a philosophical one. For the first time, we had visual proof of an object that defies visibility, a hole in spacetime itself, its presence betrayed only by the light it devoured. Behind every discovery like this lies an unseen army of computers, algorithms, and human patience. Months, sometimes years, go into decoding the whispers of the cosmos. Each pixel is earned through calibration, mathematics, and the delicate interplay between human intuition and machine logic. In the 21st century, the astronomer's most powerful instrument is not the telescope, but the model, a simulation, a recreation of the universe in silicon. These digital worlds allow scientists to test how galaxies form, how planets evolve, and how light bends under gravity. They can fast-forward billions of years or rewind to the first seconds after the Big Bang. Through this marriage of observation and computation, we are no longer just recording the universe, we are beginning to predict it. And yet, the more precise our models become, the more we realize how much we still do not know. For every pattern we uncover, there are gaps, mysteries that resist even the most sophisticated simulations. Forces we cannot see, matter we cannot touch. In the silence between the data points, a question grows louder. What if most of the universe is not light at all? For centuries, astronomy was built on a simple assumption: that what we see is what exists. Stars, planets, galaxies, these were the visible threads of the cosmos, woven together by gravity into the grand tapestry of space. But as our instruments grew sharper and our measurements more precise, a troubling realization emerged. The light we see, the entire observable universe of stars and gas, makes up less than 5% of what's actually out there. The rest, the vast, invisible majority, is something else. Something we can neither see nor touch, but whose gravity sculpts the universe itself. The first hints came not from deep space, but from the motion of galaxies. In the 1930s, Swiss astronomer Fritz Zwicky observed that galaxies within the Coma cluster were moving far too quickly to be held together by the visible matter alone. By all logic, they should have torn themselves apart. The only explanation was that some unseen mass, what Zwicky called dunkel Materie, or dark matter, was providing the necessary gravitational glue. Decades later, Vera Rubin, studying the rotation of galaxies, confirmed his suspicions. She found that stars at the outer edges of spiral galaxies moved just as fast as those near the center, a phenomenon impossible under Newtonian mechanics unless vast amounts of invisible matter surrounded each galaxy like a halo. From that moment, the universe changed. The cosmos was not a collection of shining islands floating in emptiness. It was a vast ocean of unseen substance, shaping the visible world from the shadows. Dark matter reveals itself only through gravity. It neither emits nor absorbs light, making it invisible to every telescope we have. Yet its fingerprints are everywhere, in the way galaxies spin, in the bending of light from distant quasars, and in the intricate filaments of structure that stretch across the cosmic web. Scientists have built elaborate detectors deep underground, shielded from cosmic rays, hoping to catch a single particle of this elusive substance. So far, nothing. Others search the skies for signs that dark matter might decay or collide, releasing faint flashes of gamma rays. The universe remains silent. And if dark matter is the unseen skeleton of the cosmos, then dark energy is its invisible heartbeat. In the late 1990s, two independent teams of astronomers studying distant supernovae made a shocking discovery. Instead of slowing down, the expansion of the universe was accelerating. Some unknown force was pushing galaxies apart faster and faster, as if space itself were stretching with increasing speed. That force, now called dark energy, makes up nearly 70% of the universe. We do not know what it is, only that it exists, an all-pervasive pressure embedded in the very fabric of spacetime. Einstein once proposed a similar concept, his cosmological constant, then dismissed it as a mistake. Now it stands as one of his greatest unintended predictions. Together, dark matter and dark energy form a cosmic paradox. The universe we can see is the minority. The unseen dominates everything. The stars, the nebulae, the galaxies. These are surface details, shimmering ripples on a sea of mystery. Every telescope, every detector, every simulation we build now grapples with this reality. We are trying to map a universe that hides most of its content. It's like studying the anatomy of a creature that is 95% invisible. And yet, even in the face of this darkness, the pursuit continues. Because in the absence of sight, imagination becomes our vision. Theories bloom. Perhaps dark matter is made of undiscovered particles. Perhaps dark energy is a property of quantum fields. Or perhaps both are signs that our understanding of gravity itself is incomplete. Whatever the truth, one fact is certain. The universe is far stranger and far larger than we ever believed. But in this new cosmic darkness, there is a glimmer of light, not from the past, but from the future. Humanity's next generation of telescopes and instruments will soon rise to confront these mysteries directly, with eyes sharper and farther reaching than ever before. Every discovery in astronomy is both an answer and an invitation, an answer to what once seemed impossible, and an invitation to ask again what else lies beyond. The telescopes of today have taken us to the edge of the observable universe, Yet that edge only expands as our instruments improve. The next generation of telescopes will not merely observe the cosmos, they will rewrite our understanding of it. High atop the mountains of Chile, the extremely large telescope, ELT, continues to rise from the rock and dust of Cerro Armazones. When complete, its 39-meter segmented mirror will become the largest optical eye ever built by humanity. Capable of collecting 13 times more light than any telescope before it, the ELT will peer deeper into space and farther back in time, toward the first stars and galaxies that emerged from the cosmic dark ages. But the ELT's vision will not stop there. With its adaptive optics and cutting-edge spectrographs, it will have the sensitivity to study the atmospheres of distant exoplanets, searching for chemical signatures of life, oxygen, methane, and water vapor drifting above alien skies. For the first time, we may detect not just distant worlds, but living ones. Orbiting far beyond Earth's atmosphere, the James Webb Space Telescope, JWST, is already extending this vision. Its gold-plated mirrors, cooled to cryogenic temperatures, detect the faintest heat from objects billions of years old. In a single image, Webb can capture galaxies that existed when the universe was less than 500 million years old, structures so faint that no other instrument could have seen them. What Webb has revealed so far has startled astronomers. Galaxies appear to have formed earlier and faster than models predicted. Massive structures exist where only small fragments were expected. The timeline of cosmic evolution, once so neatly arranged, is now being redrawn in light billions of years old. On Earth, a different kind of telescope is coming together, a global eye of radio and computation known as the Square Kilometer Array, SKA. When operational, it will consist of thousands of antennas spread across 2 continents, forming the most sensitive radio observatory in history. With it, astronomers will trace the faint hydrogen signals from the first billion years after the Big Bang, mapping how the earliest stars and galaxies began to illuminate the darkness. The SKA will also probe the deepest mysteries of physics, testing Einstein's theory of relativity near black holes, hunting for evidence of cosmic strings, and perhaps even detecting the faint ripples of gravitational waves imprinted on the early universe. Meanwhile, in orbit, smaller missions are preparing to fill in the gaps left by their predecessors. LISA, the Laser Interferometer Space Antenna, will soon listen for gravitational waves, tiny distortions in spacetime caused by the mergers of supermassive black holes. LUVOIR and HABEX, 2 proposed successors to Hubble and Webb, promise to combine wide-field optical imaging with exoplanet detection on an unprecedented scale, offering the possibility of seeing another Earth, not just as a point of light, but as a world with weather, oceans, and clouds. Together, these instruments form more than a technological evolution. They represent a philosophical one, a new era in which humanity ceases merely to observe and begins to participate in the unfolding of cosmic history. For the first time, we are designing machines not just to see the universe, but to understand why it looks the way it does. Each advancement pushes us closer to questions once thought unanswerable. What happened before the Big Bang? Is our universe one of many? Does life arise naturally wherever light and chemistry meet? The answers may come not as revelations, but as patterns, faint, complex, and hidden within oceans of data. The astronomers of tomorrow will need not only powerful telescopes, but powerful minds, able to see meaning in the noise, connection in the chaos, and symmetry in the unknown. As the new century unfolds, we stand on the edge of vision. The universe is not getting smaller, our eyes are getting stronger. But even as our instruments grow sharper and our reach extends across billions of light years, one truth remains. No matter how far we look, we are still searching for ourselves in the reflection of the stars. Every telescope humanity builds is more than a machine. It is a mirror, reflecting not only the light of distant stars but the nature of the beings who seek them. Across time and culture, our search for the cosmos has never been purely scientific. It is also emotional, poetic, and profoundly human. Long before technology gave us glass and mirrors, ancient civilizations gazed upward and drew stories into the darkness. The Greeks saw constellations as heroes and monsters, woven into myth. The Maya and Egyptians used the stars to build calendars of astonishing precision. In Polynesia, sailors navigated the Pacific using only the positions of the stars and the whisper of the wind. To them, the night sky was not distant. It was a map, a companion, a language written across eternity. In this way, astronomy has always been the oldest form of storytelling. Every generation has looked upward and asked the same question: what are we part of? The telescopes of today have not changed that question. They have only deepened it. When the Hubble Deep Field was first released in 1995, a small patch of sky no larger than a grain of sand held at arm's length, it revealed more than 3,000 galaxies, each containing billions of stars. That single image redefined our sense of scale. The cosmos was not just vast, it was overflowing. Every speck of darkness we had ever dismissed as empty was, in truth, filled with light too distant to see. To many, that realization was humbling. To others, it was spiritual. The poet and astronomer Carl Sagan once said, "We are a way for the cosmos to know itself." In that idea lies the quiet, astonishing paradox of astronomy. That consciousness, the fragile, fleeting spark of awareness that exists on one small planet, has developed the ability to understand the infinite. The modern age of astronomy, with its satellites and supercomputers, might seem distant from myth and meaning, but the impulse remains the same. When the James Webb Space Telescope captures a galaxy as it appeared 13 billion years ago, we are not just observing history, we are witnessing our own origins. Each photon that strikes a detector is a message that has traveled across cosmic time, surviving explosions, collisions, and expansion, only to arrive in our hands. In that moment, technology becomes ritual. The act of observation becomes a kind of reverence, a silent acknowledgement that we are both infinitesimal and essential. The cultural echoes of this understanding reach beyond science. They shape how we think about time, creation, and our place in existence. Artists reinterpret the imagery of the cosmos in paint, sound, and film. Philosophers debate whether the universe has consciousness or meaning. Children learn that the atoms in their bodies were once forged in stars, and in that realization, something ancient stirs, a connection that transcends generations and geography. Even the languages of faith and science begin to intertwine. Where once the heavens were the domain of gods, they are now the realm of equations and data. Yet the awe remains. The more we know, the more the mystery deepens. The more precisely we measure the universe, the more impossible it seems that we exist within it at all. And so, every telescope, every lens, every dish, every array, is part of an unbroken human tradition. The attempt to understand the infinite by building something finite that can point toward it. But there is one final step in that journey, one frontier that no telescope, no machine can cross. A horizon not of light, but of perception. It is the moment when discovery turns inward, and the universe we study becomes the universe we remember. Every light we see in the night sky is a message from the past. Some left their source before the Earth even formed, before our sun was born, before the Milky Way was what we know today. When we look outward, we are also looking backward, across time, across change, across the long decay of light itself. But one day, even this will end. The universe is not static. It is expanding. Galaxies drift farther apart. Their light stretched thinner and fainter with every passing moment. Billions of years from now, most of the galaxies we see today will slip beyond our cosmic horizon, receding so fast that their light will never reach us again. To future astronomers, the night sky will grow emptier, the stars fewer, the universe lonelier. This idea, known as cosmic isolation, is not poetic exaggeration, it is physics. As dark energy continues to drive the universe's expansion, every cluster of galaxies will become an island, sealed off by distance and time. Even if life endures, the evidence of its origins will fade from view. The cosmic background will cool to invisibility. The great map of the universe will dissolve until nothing but our local stars remain. It is a haunting thought that one day the universe will erase its own history. And yet, perhaps that is what makes our era so extraordinary. We exist in the brief window when the universe is still readable, when ancient light still reaches our eyes. Humanity, in cosmic terms, has arrived at exactly the right moment, late enough for stars and galaxies to have formed, early enough to still see them. We are witnesses to a fleeting clarity. Telescopes like Hubble, Webb, and the ELT do more than record this light. They preserve it. Every image, every measurement, is an act of cosmic archiving, a way of saving the universe's memory before it fades into darkness. When we look at the earliest galaxies, we are not only learning about their birth, we are safeguarding the last traces of the first light. But perhaps even that light will not be the end. Some theories suggest that as stars die and black holes evaporate, the universe will enter a new phase, a dark era, where matter itself disintegrates and the cosmos becomes a sea of faint radiation. In that final age, light will no longer travel between stars. There will be no stars to shine. The universe will become quiet. And yet, even in such silence, there is meaning, because the act of seeing, of searching, is itself the universe becoming aware of its own beauty. Through our instruments, through our questions, the cosmos briefly becomes conscious of its own existence. Maybe that is what the last light truly means, not the end of illumination, but the end of ignorance. The moment when a fragment of the universe, calling itself human, learns to understand where it came from. Our telescopes may one day fall silent. Our civilizations may vanish. But for now, in this small moment of clarity, we are here, awake in a universe that is still speaking in light. And that may be enough. Every story of discovery ends where it began, with darkness. The same darkness that once frightened our ancestors now surrounds us at the edge of knowledge, vast and infinite. But this darkness is no longer emptiness. It is potential. It is the canvas on which the universe continues to write. In the span of a few centuries, humanity has gone from watching the stars with naked eyes to building machines that can see back to the dawn of time. From Galileo's trembling telescope to the golden mirrors of James Webb, each invention has extended not just our vision, but our understanding of existence itself. We have peeled back layers of the cosmos like pages in a book, each one revealing not answers, but deeper mysteries. And in those mysteries we have found ourselves. The atoms in our bodies were born in the hearts of long-dead stars. The iron in our blood was forged in supernova explosions. The calcium in our bones once drifted through interstellar clouds before finding a home on Earth. We are not observers of the cosmos, we are its continuation. When we turn our telescopes outward, we are, in a sense, looking inward back through time, back into the origins of our own being. Every distant galaxy, every faint photon, is a reflection of the same processes that made us possible. The cosmos is not out there. It is within us. This realization carries a quiet responsibility. The universe does not need us to exist, but through us, it becomes known. Through curiosity, patience, and wonder, we give the void a voice. And in doing so, we create meaning where there was none. Long after our telescopes fall silent, their legacy will remain. Not in the metal and mirrors, but in the knowledge they left behind. The data, the images, the understanding, they will echo across generations, a record of how one small species dared to understand everything. Perhaps, someday, others will rise from another world, look toward our faint sun, and wonder who we were. Perhaps they will find traces of our machines, still orbiting in the dark, silent witnesses to a civilization that once looked at the stars and refused to stop asking questions. And maybe, in that distant future, the cycle will begin again. A new intelligence, born from the same cosmic dust, will rediscover the light, rebuild the lenses, and reopen the eyes of the universe. Because the story of seeing is not the story of humanity alone. It is the story of life itself, reaching toward understanding. The cosmos awakens through those who look, and sleeps through those who forget. In the end, there may be no final frontier, only new ways of perceiving what has always been there. The light, the darkness, and the endless dance between them. And so the last question remains, quiet but eternal. When the universe looks back through us, what does it see? In the silence between galaxies, light continues its endless journey. Ancient, patient, unstoppable. It travels through the void long after the stars that created it have died, long after their worlds have cooled and their suns have faded into memory. Every photon carries a story, and when it reaches us, we become its reader. This is the quiet miracle of existence. The universe, through us, learns to see itself. When the first humans looked up at the night sky, they saw patterns, shapes drawn in stars, myths etched across eternity. Today we see data, wavelengths, spectra. Yet at the heart of both is the same desire, to make sense of the infinite, to find meaning in the darkness, to understand where we are and what we are made of. The telescopes we build, whether carved from metal, glass, or mathematics, are not merely instruments of observation. They are acts of faith. Faith that the universe is knowable, that truth exists beyond perception, that order hides within chaos. Each beam of light we capture, each image we decode, is a reaffirmation that knowledge and wonder can coexist. And when we turn those instruments toward the farthest reaches of the cosmos, we discover that the line between the observer and the observed begins to blur. The galaxies we study are not separate from us. They are kin. The light that left them billions of years ago is now part of our own awareness. The act of looking transforms both the universe and the one who looks. In this way, we are part of an infinite mirror, light reflecting light, consciousness observing consciousness. The cosmos is not a cold expanse, but a self-aware unfolding, in which matter becomes mind and mind becomes meaning. Our machines, our mathematics, our myths, all are fragments of this mirror. Even when the stars fade, the reflection remains. It exists in every question we ask, every experiment we build, every dream that begins with someone simply looking up. One day, our civilization will pass, as all things do. The telescopes will fall silent, their mirrors coated in dust, their sensors frozen in shadow. But the light they captured will still travel onward, out into the void, carrying with it the proof that, for a brief moment, the universe knew itself through us. And somewhere, perhaps, that light will find another set of eyes. Until then, we remain the keepers of the mirror, the storytellers of starlight, the children of ancient fire, the brief but brilliant witnesses of eternity. The universe has always been watching. Now, finally, it can see. There comes a moment after the data are gathered, the equations balanced, and the images rendered when silence returns. The telescopes rest, the domes close, and the night reclaims its quiet dominion. Yet in that silence, something lingers, a realization so vast and simple it transcends language. We have spent centuries learning how to see, and in doing so we have learned who we are. From the first lens ground by Galileo's trembling hands to the golden mirrors of James Webb, every step forward has been an act of defiance against blindness, against the limits imposed by our smallness and our time. We were never content to look only as far as our eyes allowed. We built new eyes, forged from curiosity and courage, and through them, we turned darkness into revelation. What we discovered is not a universe that answers all questions, but one that invites them endlessly. Every photon of light leads to another mystery. Every discovery opens 1,000 doors. The cosmos is not a solved equation, it is a living conversation. And the voice speaking through it is not only mathematical or mechanical, it is deeply human. Because behind every telescope is a heartbeat. Behind every data point, a pair of eyes filled with wonder. The universe does not know it is beautiful. It needs witnesses to beauty for beauty to exist. That witness is us. Our species may be fragile, our time brief, but for this moment, this shining moment in cosmic history, we have achieved something extraordinary. We have made the universe self-aware. Through our instruments, the cosmos reflects upon itself. Through our thoughts, it contemplates its own origins. Through our art, our science, and our awe, it learns to speak in new forms. We are both its expression and its echo. And though the stars will one day fade, though light will stretch thin and the galaxies drift apart, the act of perception itself is eternal. For once consciousness has emerged in the universe, it can never be undone.